Here we'll use solve linear systems by something called determinants. The determinants are supremely good for 2x2 systems, pretty good for 3x3, but higher, you might as well use row operations. Okay, we start with this system. Ax plus by equals e, cx plus dy equals f. And we'll use row operations to solve it. Okay, first, to eliminate the y, we have a by and a dy here. So we'll rescale this row by d and this row by b. So these will line up, b dy and minus b dy. So this rescaled by d is adx plus bdy equals ed. This rescaled by negative b is minus bcx minus bcy equals minus bf. When we add these two equations together, the y term cancels. We eliminate it. We get AD minus BC times x equals ED minus BF. And so dividing, x equals ED minus BF over AD minus BC. That's what I call a closed form solution. You don't have to go through all the steps. Here it is in one freeze-dried package. You just add water and stir. Oh, no, to get y, well, we have an AX and a CY. So to make them line up, we'll rescale the first row by a negative C and the second row by an A. You get minus ACX minus BCY equals minus EC. Second equation becomes ACX plus ADY equals AF. If we add these equations together, then the x terms cancel, minus ACX plus ACX cancels. Add these together, you get AD minus BC times y equals AF minus EC. That's curious. This is the same as this. Then we divide, we get y equals AF minus EC over AD minus BC. Okay, we have a formula. We don't have to go through steps. We just plug them in and turn the crank, and out comes an answer. The main difficulty right now is, how do you remember this? It's not that obvious. Well, hold on. Everything here is a difference of products. It's the same difference of products here. And these, and for this and this, E stands in for A and F replaces C. Here, F replaces D and E replaces B. So here's what we do. We make a specific notation for this thing here, AD minus BC. We call it the determinant of a 2x2 matrix. So the determinant of RSTU is product along the main diagonal, RU, minus product along the opposite diagonal, ST. To make a dreadful pun, this is so you won't get rusty. Okay, the idea is this. From this, if you define this symbol this way, product along main diagonal minus product along opposite diagonal, then this formula translates into this Cramer's rule. For this 2x2 system, x equals this determinant over this determinant, y equals this determinant over this determinant. In both of them, we have the determinant of A, B, C, D, the determinant of the coefficient matrix. For x, we'll put EF, for x, the first variable, we'll put EF in the first column, EBFB. For y, the second variable, we'll put EF in the second column, AECF. So that's it. For example, so here we do some examples. Determinant of 2, 3, 2, 5. 2 times 5 minus 2 times 3, that's 10 minus 6, or 4. Negative 6, negative 2, 15, 4. Its determinant is negative 6 times 4 minus 15 times negative 2. That's negative 24 plus 30 is 6. Okay, so those are examples of determinants. To solve x plus y equals 6 and x minus y equals 2, here's what we do. For x and y, we put the determinant of 1, 1, 1, negative 1 in the denominator. For x, we put 6, 2 in the first column, 6, 1, 2, negative 1. For y, we put 6, 2 in the second column, 1, 6, 1, 2. So, okay. And, okay, 6 times negative 1 is negative 6, minus 2 times 1 is minus 2. 1 times negative 1 is minus 1, minus 1 times 1 is a 1, is minus a 1. To get negative 8 over negative 2 is a 4. For y, 1 times 2 is 2, 1 times 6 is minus 1 times 6 is a minus 6. Over the same negative 2, so you get 4 over negative 2 is a 2, and there you go, x is 4, y is 2. And the beauty of this is we just like I say, we just substitute into into here and use the definition of determinant. And there's no algebra left after that. It's just a bunch of arithmetic. Here's 3x minus 4y equals 9, x plus 2y equals 8. Okay. So the matrix, the coefficient matrix is 3, negative 4, 1, 2, which we put here in its determinant. For x, we put 9, 8 in the first column. So we put 9, negative 4, 8, 2. For y, we put 9, 8 in the second column, 3, 9, 1, 8 here. So let's first do the denominator. 3 times 2 is 6, minus 1 times negative 4 is 6 minus negative 4, which is a 10 here and here. For the numerator, 9 times 2 is 18, minus 8 times negative 4 is minus a negative 32. That's 50. 50 over 10 is 5. For y, 3 times 8 is 24, minus 1 times 9 is minus 9. That's 15 over a 10. 10 is 1.5. So x is 5, y is 1.5. Here we have 3x plus 2y equals 11, 6x plus 4y equals 11. So the coefficient matrix is 3, 2, 6, 4. And we put 11, 11 in the main column, in the first column. So 11 times 4 is 44, minus 11 times 2 is minus 22. Into the denominator, 3 times 4 is 12, minus 6 times 2 is 12. Whoops, 12 minus 12 is 0. You get 22 over 0, which is infinity. Now, when you get a 0 in the denominator and an infinite value for x or y, then that means there's no solution, and the equation in the system graphs is parallel lines where there's no intersection. So Cramer's rule does signal when there's a no solution system. Here's 3x plus 2y equals 11, 6x plus 4y equals 22. Well, 3, 2, 6, 4 as below. 3 times 4 is 12, minus 6 times 2 is 12 is 0. Dividing by 0. 11, 22 in the first column. 11 times 4 is 44, minus 22 times 2 is 44. So you get 0 over 0. Instead of non-zero over 0, which is infinite, you get 0 over 0, which is an indefinite ratio. Here, the graph is of 2 lines overlapping, which therefore intersect along their entire lengths. So there's many solutions. So you have the no solutions case, which is signaled by an infinite answer. And there's a many solutions case, which is signaled by a 0 over 0 indefinite answer. Now you can do the same thing for 3 by 3 and 4 by 4 and so on. I'll give you the relatively simple formula for 3 by 3 and the increasingly burdensome formula for higher determinants. Here we go. We have a 3 by 3 matrix, A, B, C, D, E, F, G, H, I. Its determinant, we do this. We write the matrix, then we write the first 2 columns outside like that. ADG, ADG, BEH, BEH. And then you take products along the downward diagonals minus the products along the upward diagonals. AEI plus BFG plus CDH minus GEC minus HFA minus IDB, like that. It's sort of like the 2 by 2 thing with main diagonal minus upward diagonal. So it looks a lot the same thing. It doesn't work for 4 by 4 and up, sorry to say, but it does work for this. So then the 3 by 3 Cramer's rule is a lot like the 2 by 2 Cramer's rule. We have AX plus BY plus CZ equals J, DX plus EY plus FC equals K, GX plus HY plus IZ equals L. For X, Y, and Z, put the A, B, C, D, A, F, G, H, I determinant in the denominator. For X, the first variable, we put J, K, L in the first column. Y, we put J, K, L in the second column. And Z, we put J, K, L in the third column. And ratios the determinants of the answer. So, for example, 1, negative 4, 1, 3, 0, negative 2, 3, 1, negative 2. What is that determinant? Well, we write these here, and we put 1, 3, 3 up here, negative 4, 0, 1 here. Okay, downward diagonals. 1 times 0 times -2, plus 4 times -2 times 3 here, plus 1 times 3 times 1 here, minus 3 times 0 times 1 here, minus 1 times -2 times 1 here, minus -2 times 3 times -4 here. Okay, 0 plus 24 plus 3 minus 0 minus a -2 minus a -24, which after a bunch of arithmetic is 5. Here we have a simple 1, 1, 2, 0, 1, 2, 0, 1 determinant. We write it down here, and then we write down 1, 0, 0 here, 2, 1, 0 here. 1 times 1 times 1 is a 1. 2 times 0 is a 0. 0 times 0 times 0 is a 0. Minus 0 times 1 times 0 is a 0. Minus 0 times 2 times 1 is a 0. Minus 1 times 0 times 2 is a 0. Relatively simple, you just get a 1. So, here we have x plus y plus z equals 4, x plus y minus z equals 0, x minus y plus z equals 2. So the coefficient matrix 1, 1, 1, 1, 1, -1, 1, -1, 1 from here. And after its determinant is -4. If we put 4, 0, 2 in the first column, then after a bit of work from its determinant, you get -4. And so x is this -4 divided by this -4, which is a 1. With 4, 0, 2 in the second column here, then you get -4, and y equals this -4 divided by this -4 is a 1. You put 4, 0, 2 in the third column here, then this minus this comes out to -8. So z is -8 over -4, which is a 2. So there we are. X is 1, y is 1, z is 2. Well, okay. This is to solve 3x3 systems this way is well, it's feasible. It's perhaps a little better than using row operations. If you can use it, if you're willing to use a matrix inverses and a calculator, that also works. For higher determinants, it's a mess. If you look, you can look at, you can use, excuse me, try work, excuse me. To find a 3x3 determinant, you can do what's called expand along a row or a column. Here we go, A, B, C, D, E, F, G, H, I. Let's say we can expand along A, B, C. We have A times what's left, E, F, H, I, like that. Minus B times, eliminating its row and column, D, F, G, I. Plus C times D, E, G, H. Notice we have plus A minus B plus C. So there's some alternating happening in determinants inherently. Now that's if I'm expanding along this row. If I expand along this column, I get A times EFHI minus D times BCHI plus G times BCEF. In each case, you multiply a term by the matrix left over when you eliminate its row and column. And then plus minus by this kind of checkerboard. Here, let's expand along, say, this row. Minus D, because it's a minus, times BCHI, that's what's left over, plus E times ACGI here, minus F times what's left, ABGH. So it looks like an alternating Solomon difference of terms along a row or a column times minors, which are determinants of what's left in the matrix when you eliminate that row and column. A mess, I agree. If here's a 4 I can do similarly a 4x4 determinant. Let's say expand along this row here. A times what's left over here, FGH, JKL, NOP, minus B times EGH, IKL, MOP, plus C times EFH, IJL, MNP, minus D times EFG, IJK, MNO. And you can, the difficulty is this, you get ever more terms because each of these needs to be expanded. For a 3 by 3 determinant, you ultimately wind up with 6 terms. This is 2 terms times 8, that's 2 terms, plus another 2 terms, plus another 2 terms, it's 6. For 4, it's 24 terms. For a 5 by 5 determinant, it's 120 terms. It grows up very quickly, and therefore is not that useful for the higher matrices. Oh, there's one more thing. Area of a triangle in the plane. Given 3 points of a triangle, A1, B1, A2, B2, A3, B3. Its area will be plus or minus a half times A1, B1, 1, A2, B2, 1, A3, B3, 1. Plus or minus to make it positive, because a determinant can be negative. So for example, the points 1, 2, 2, 1, and 5, 5. What's the area? Well, a half times 1, 2, 1, 2, 1, 1, 5, 5, 1 determinant. And if you expand this out, you get 7, so the area is 7 halves. There's a problem in the homework involving 3 points. What's the area? This is the formula. Okay, that concludes this. And we'll